Okay, so this worksheet is going to be our notes for section 3.7. We're going to talk about rational functions in this section. So there's a definition there. It says the rational function is a function of the form f of x equals p of x divided by q of x, where p of x and q of x are polynomial functions and q of x is not the zero polynomial. So just like with numbers, I can't divide by 0. When graphing a rational function, which is what we're going to do in this section, we have to consider any vertical, horizontal, or oblique asymptotes. Okay, now an asymptote is a linear boundary that the graph approaches, but it's never going to get there. Okay, so I next talk about how to find the vertical asymptotes and the horizontal or oblique asymptotes. Okay. VA is going to mean vertical asymptotes, HA is going to mean horizontal asymptotes, and OA is going to mean oblique asymptotes. To find the vertical asymptote, so it says the rational function f of x equals p of x divided by q of x, which has to be in lowest terms. Now that's key for this section, okay? And one of the problems, you're going to have to make sure that you've simplified before you identify the vertical asymptotes. Okay, so it says that a rational function will have a vertical asymptote x equals k if k is a real zero of the denominator q of x. Okay, so all you're going to do is you're going to basically just state the domain of the function. Any number that you're throwing away as a result of the domain is going to create vertical asymptotes on the graph. Okay? Now to get horizontal or oblique asymptotes, it's totally different. You don't just look at the domain, but instead you have to compare the degree of the top to the degree of the bottom. The degree is the largest power of x that appears. Okay? And item 1, it says if the degree of the top, p of x, is less than the degree of the bottom, q of x, then y equals 0 is going to be a horizontal asymptote. There's no work to do. You're just going to write y equals 0 is the horizontal asymptote. Okay? Item 2, if the degree of the top is the same as the degree of the bottom, then that means that there's going to be a horizontal asymptote. It's not going to be at y equals 0. It's going to be at y equals c. And to find the value of c, you're going to divide p of x by q of x and then disregard the remainder. I'll talk about why we're disregarding the remainder after we look at some examples here. Okay. And then item 3 says that if the degree of the top is 1 more than the degree of the bottom, then y equals mx plus b is an oblique asymptote. Think of an oblique asymptote as a slanted boundary. Okay? To find the values of m and b, you're going to, again, divide, and then, again, disregard the remainder. Okay? So let's take a look at these two examples here. So there's two, I guess, common ways that you can graph a rational function. One is to use the information that you know about transformations. Okay, and then the other is to use a list of steps. I talk about those two things on the next page. The graphs of the two basic functions y equals 1 over x and y equals 1 over x squared are shown below. Determine the key features of each graph. Okay, so there's the graph of y equals 1 over x. Here's the graph of y equals 1 over x squared. So what I mean by key features is like the domain, the range, the intercepts, any asymptotes that are on the graph, and if the function is even or odd. Okay, so let's try y equals 1 over x. Y equals 1 over x, the domain is all real numbers except for 0. I see x is in the denominator. I know I can't divide by 0, so just don't let x be 0. Okay, x can be any other number. Now, because I'm throwing 0 away as a result of the domain, I know that there's going to be a vertical asymptote on the graph at x equals 0. Okay, so go ahead and draw a dotted line right on the y-axis there when x is 0. And the dotted line represents an asymptote. So an asymptote is just a boundary that the graph gets closer and closer to, but it's never going to get there. Okay. The range of the function, so, well, I can't plug 0 in for x. There's no other number that I can let x be that's going to return 0. So y can't be 0. Okay? Because y can't be 0, I draw a dotted line on the y-axis. Okay? So y equals 0 is a dotted line there, and that again represents an asymptote. So the curve is going to get closer and closer to those boundaries, but it's never going to get there. Okay? Now, a horizontal asymptote, I'm comparing the degree of the top to the degree of the bottom. The degree is the largest power of x that I see. So with y equals 1 over x, the degree up top is 0. I don't have any x's up top. And the degree of the bottom is 1. 0 is less than 1. So y equals 0 is going to be a horizontal asymptote. Okay, and that's what we got here. What are the intercepts? Well, there are none. That's what I was just talking about. Okay, so x can't be 0 and y can't be 0. Okay, so at no point will the graph cross or touch the x or y axes there. Okay, now when they're asking for the asymptotes, the vertical asymptotes or the horizontal or oblique asymptotes, you always want to give your answer as equations. Okay, so I've got a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. I would not just write 0. Okay, because 0, that's misleading. You know, are you talking about x equals 0 or y equals 0? Well, for here, it didn't matter, you know, but for like many other examples, it will matter. Okay, so always write the asymptote as an equation. Okay, x equals whatever number and y equals whatever number. Okay, is this function even or odd? Well, this is going to be an odd function because it's symmetric to the origin. And that's really the only reason why we care about if a function is even or odd is because there'd be some symmetry involved in this. So an even function is symmetric to the y-axis. An odd function is symmetric to the origin. Okay, and symmetric to the origin just means that any point that's on the graph, x, y, negative x, negative y would be on the graph also. So like here's 1, 1 is on the graph, negative 1 is also on the graph, right? Okay, that'd be an odd function there. And yeah, here's another basic function, y equals 1 over x squared. So the domain of y equals 1 over x squared is all real numbers except for 0. Again, I can't divide by 0, so just don't let x be 0. Because I'm not letting x be 0, I'm going to have a vertical asymptote at x equals 0. So go ahead and draw a dotted line right at x equals 0, and what we're saying is that the curve is going to get closer and closer to x equals 0, but it's never going to get there. Okay? The range of the function is all positive numbers. So if I scan the y-axis, anything that is bigger than 0, if I look to the left or the right, I'm going to be on the curve. Anything that's 0 or less, I don't have any graph down here, right? Also, y can't be 0. Okay? So x can't be 0 also, right? But there's no other number for x that is going to return 0. Okay? So y is going to be strictly bigger than 0 there. The intercepts, there are none. That's what I was just talking about. Okay? So x can't be 0 and y can't be 0. Well, an intercept is a point where you're going to cross or touch the coordinate axes, right? And that's not going to happen here on this graph. Okay, we've got a vertical asymptote at x equals 0, okay, and there's a horizontal asymptote at y equals 0. And just, again, to kind of tie in what I've mentioned up here, the vertical asymptote is going to be any number that you're throwing away as a result of the domain. So because I'm throwing away 0, I know that there's going to be a vertical asymptote at x equals 0. And to get the horizontal asymptote, I compare the degree of the top to the degree of the bottom. So with 1 over x squared, the degree, the largest power of x that I see up top, is 0. I don't have any x's up top. And I'm dividing this by a degree 2 polynomial. So 2 is bigger than 0, right? And because of that, y equals 0 would be a horizontal asymptote. And again, there's no work to do. You just write y equals 0, okay, and draw the dotted line there at y equals 0. Okay, is the function even or odd? Okay, well this is going to be an even function because it's symmetric to the y-axis, right? If we spin the graph about the y-axis, we'll get the same picture. Okay. Let's take a look at the next page there. So in problem 1, they want us to graph the function g of x equals 1 over x minus 2 plus 1 by using transformations on y equals 1 over x. Okay, so there's the graph of y equals 1 over x, which is, on this page here. And so I just redrew that, right? We know that x equals 0 is a vertical asymptote and y equals 0 is a horizontal asymptote. We just said that back in this problem. So using transformations, what does it mean if I replace x with an x minus 2? I'm going to have to shift the graph to the right 2 units. And then the plus 1 means I'll have to shift the graph up 1 unit. Okay, so there's going to be 2 shifts on this graph of y equals 1 over x to get the new graph. You're going to have to go to the right 2 and up 1 with all these points. Okay, well, if we do that, 1, 1, when I go to the right 2 and up 1, that would put me at 3, 2 on the new graph. Here's a negative 1, negative 1 on the original graph. When I go to the right 2 and then up 1, that point would be at 1, 0 on the new graph. Okay, so all the points are going to move to the right 2 and up 1, including the asymptotes. Okay, so I've got a vertical asymptote at x equals 0. When I go to the right 2 and then up 1, now going up 1 isn't going to change anything, but I'm going to shift this vertical asymptote to the right 2, and I would have a vertical asymptote at x equals 2. Okay, again, make sure that's written as an equation. I would not just write 2, because that can be misleading. You know, if I were to just write 2, somebody could think that I'm talking about y equals 2. Well, y equals 2 is different from x equals 2, right? So x equals 2 would be the vertical asymptote. Okay, and then to get the horizontal asymptote, I would start with here's y equals 0, and I'm going to the right 2, which doesn't change anything, but then going up 1. So ultimately, the horizontal asymptote is going to be at y equals 1. And I draw a dotted line there. Okay, so y equals 1 is the horizontal asymptote. Okay, and this here would be a quick rough sketch of the graph of g of x. Okay. Problem 2, I want us to graph the function g of x equals negative 1 divided by x plus 1 squared by using transformations on y equals 1 over x squared. Okay, so we drew the graph of y equals 1 over x squared. That's this guy here. And when you use transformations on that, I redrew the graph just so that we have it here. Now, what does the negative up top mean? Well, that means I'm going to have to reflect the graph about the x-axis. Okay, so flip it upside down, and then x is being replaced with x plus 1. If I do that, I'm going to have to shift the graph to the left 1 unit. Okay, so there's two transformations that happen here with this graph. You're going to first flip the graph upside down and then shift it to the left 1 unit with all these points. So let's see where some of them are going to land. Here's 1, 1 on the original graph. When I reflect that about x, that puts me at 1, negative 1. And then when I go to the left 1, that'll put me at 0, negative 1. Okay, so the point that was at 1, 1 is now going to be at 0, negative 1 on the new graph. Here's the point negative 1, 1. So when I flip that about the x-axis, that puts me at negative 1, negative 1. And when I go to the left 1 unit, that brings me to the point negative 2, negative 1 on the new graph. Okay, so all these points are going to move, including the boundaries. So, I got a vertical asymptote at x equals 0. When I reflect this about the x-axis, that's not going to change anything, but I'm going to shift that boundary to the left 1 unit. So ultimately, I'm going to have a vertical asymptote at x equals negative 1. Okay? And then to get the horizontal asymptote, flipping the graph about the x-axis is not going to change anything. And then also shifting it to the left 1 unit is not going to change anything. So I'm still going to have a horizontal asymptote at y equals 0 there. I draw a dotted line right on the x-axis. Okay? Now, there's nothing new with what I'm showing you here. Okay, like we've already talked about transformations, right? So I guess the only new thing would be the concept of an asymptote, right? Now, quite honestly, it's going to hardly ever be the case that if I give you any function, that you're going to be all set up in a nice, convenient manner to use transformations on that. That's hardly ever going to happen. Okay, so to me, like the more important thing here is going to be this other way to graph a rational function, which is just to use a list of steps. Okay, so we'll talk about that in the next video there. And we'll go ahead and stop this video right here.